So in the previous lecture, we extended a function mu, which was defined on a semi-algebra and taking values in R plus union plus infinity. So we extended this function to a function u, which is defined on the algebra generated by the semi-algebra S. And we've seen that if mu was additive, then the extension was additive. If it was sigma additive, the extension was sigma additive, and that the extension is unique. So the goal of today's lecture is to show that once we have a function which is sigma additive defined on an algebra, we can extend it in a unique way under certain conditions to a measure, so a function which is defined on the sigma algebra generated by the semi-algebra in a unique way. So this function will take values on R plus union plus infinity. It's an extension, so its restriction to the algebra will be equal to pi, and it will be sigma additive. So this is the goal of the lecture today. So we start with a function which is sigma additive defined on an algebra, and we want to extend it to a function defined on the sigma algebra generated by the algebra, which corresponds to the sigma algebra generated by the semi-algebra, and we will show that this extension is unique. So what we will do is the following. We will start by defining a function p star. So remember that all these semi-algebras, algebra and sigma algebras, are algebras of subsets. So there exists a starting set omega, and all these algebras and semi-algebras are algebras and semi-algebras of the subsets of omega. So we will define p star in all subsets of omega. And we will prove that p star, it's not a measure, but it's an outer measure. And this I will define in a second. So the first step will be to prove that p star, it's what we will call an outer measure. Then we will introduce a set, which is the set of the measurable subsets of omega. So M will be a family, a class of subsets of omega. And we will show that this class, it's in fact a sigma algebra. That it contains the algebra, and therefore, since it's a sigma algebra, it contains also the sigma algebra generated by the algebra. That if you consider the outer measure p star restricted to the set M, then it's sigma additive. That p star restricted to the algebra coincide with the measure from which we started from. So p star restricted to M, which is a sigma algebra which contains the algebra, is therefore an extension of nu. And finally, we will prove that this extension is unique under certain conditions. So this is the plan of the lecture today. We'll first define this outer measure. Then we will introduce a set of subsets, so a class of subsets of omega. We will show that this class forms a sigma algebra, that it contains the algebra, that p star restricted to this class, it's sigma additive, and that p star restricted to A, it's equal to nu, and that therefore P star restricted to M, it's an extension, and that that this extension is unique in the sigma algebra generated by the algebra under certain additional conditions. So this is the plan of the lecture today. So step 1, we will define P star. So I want to define P star on P lambda, so all the subsets of lambda taking values in R plus union plus infinity. So let's take a subset A of omega, and I will define P star of A. So here is the way in which we will define. Well, consider class of functions, countable class of sets, which belong to the algebra. So each EI belongs to the algebra, and consider this class in such a way that the set A, it's contained in the union. So let's take, since EI it's an element of the algebra, nu of EI it's well defined, let's take the sum of nu of EI. Note that this class, it's non-empty, because we can always take E1 to be omega and E2, E3, and so on to be the empty set. So we have at least one way in which we can cover the set A by elements of the algebra. Since this set is non-empty, now let's take the infimum over all such coverings. So I'll say that EI, it's a covering if each set EI belongs to A, to the algebra, and if the union of EI contain A. Note here that I'm not requiring these sets EI to be disjoint. They can have intersections. Let's take the infimum over all this class, and let's define P star A to be the infimum. So this is the definition of P star, and observe that it's defined for any subset of omega. So now let me define an outer measure. So I'll say that a function mu, which is defined on a class C, and which takes value on R plus union plus infinity, where C is some class of sets of subsets of a certain set omega. So let's say that mu, we will say that mu it's an outer measure if, well, I will assume that the empty set belongs to C. We will require mu of the empty set to be equal to 0. We will require mu to be monotone, which means that if E is contained in a set F, E and F in C, then mu of E it's less than or equal to mu of F. So mu, it's monotone. And finally, instead of the sigma additivity, I will require sigma subadditivity, which means that if I have a set E and sets EI belonging to the class C, and if E it's contained in the union of EI, then I will require mu of E to be less or equal than the sum of mu of EI. So here is the definition of an outer measure, a function defined on a class C of sets will be called an outer measure if it satisfies these three conditions. And my first claim is that P star, defined by this formula, is indeed an outer measure. So let's prove that. So let's prove that P star is an outer measure. So there are three conditions which need to be proved. The first one is that P star of the empty set is equal to 0. Well, on the one hand, the empty set, so if you take EI to be equal to the empty set, it's clear that EI is a covering of the empty set, and therefore that P star of the empty set, which is the infimum, is less than or equal to the sum of nu of EI, but EI is the empty set, nu of the empty set is 0, so this is equal to 0, and this proves that P star of the empty set is less than or equal to 0. On the other hand, since if you take any covering of the set, of the empty set, so let's take a covering EI in A, the empty set included in EI, this expression, the sum of nu EI, since nu takes only non-negative values, this is always greater or equal than 0. In particular, if you take the infimum of all possible coverings of the empty set, you get a non-negative number, which therefore implies that P star of the empty set is greater or equal than 0. Therefore, P star of the empty set is less than 0, it's greater than 0, which gives you that P star of the empty set should be equal to 0, and this proves the first condition. Now, let's go to the second condition. So let's consider set E contained in a set F, and we have to prove that P star of E is less than or equal to P star of F. Well, that's very easy. Let's take any covering EI of the set F. This means that these sets EI belong to the algebra, and that F is contained in the union of EI. Well, any covering of the set F, it's also a covering of the set E, because F contains E. This means that when I define, let me write it here, when I define P star of E, I'm taking an infimum over all coverings of the set E of nu EI. While when defining the set F, I'm taking all coverings of the set F. But since any covering of F is also a covering of E, the class of coverings here, it's larger than this class. Since this class is larger, when taking the infimum, we get something which is smaller than this one. right? Here, the family of coverings of F, any such covering is also a covering of the set E, and therefore belongs to this class in which we are taking the infimum, which means that this infimum is less than or equal to that one, which means that P star of E is less than or equal to P star of F, which is what we wanted to prove. So here's this inequality, just a simple observation that any covering of F, it's also a covering of E. This proves the second inequality. The second property of outer measure. So let's finally go to the third property of outer measures. Well, here we are taking a set E, which is contained in the union of the sets EI, I union for I greater or equal than 1, and we want to show that P star of E is less than or equal to the sum of I greater or equal than 1 of P star EI. Well, to prove this inequality, we can, of course, assume that P star of EI is finite for all I, right? If P star of EI is equal to plus infinity for one I, the right-hand side is plus infinity, and this inequality is trivially satisfied. So we can assume that P star of EI is finite. Well, if P star of EI is finite, by definition of P star, we can find a covering which is almost equal to P star of EI. Let me make it more precise. So let's assume that P star of EI is finite. Let's fix some epsilon positive. And remember that P star of EI is given by the infimum over all coverings. So let's say that we are covering with sets HK of the set EI. So HK are elements of the algebra, and the union of HK contains EI of the sum of HK. And so what I claim is that since this infimum, by assumption, it's finite, we can find a covering which almost attains this infimum. What do I mean by that? Well, there exists a covering which I will call HIK. HIK belongs to the algebra for each k. EI, it's contained in the union of HIK. And P star of I, which is the infimum, therefore it's less than or equal to the sum over k of nu HIK. But this infimum, so this sequence, this covering of the set EI almost attains the infimum in the sense that it's less than or equal to P star of EI plus, let's say, epsilon to the 2 at power I. So we can, since this infimum is finite, we can always find such a covering. That's nice, because now if I take, so each family, it's a covering of EI. So if you take the union of all these families, we still get a countable sets, a family of sets, which are all in the algebra. This union over I will be a covering of the union of EI, but since the union of EI contains E, the family HIK, it's a covering of the set E, right? Because they are all elements of the algebra, and the union over I and K contains the union over I of EI, and the union over I of EI contains E. So this is a covering of E. If it's a covering, since P star of E is the infimum, P star of E is less than or equal to the sum over I and K of nu H I K. Right, because H I K forms a covering of the set E. Then, if you now observe that the sum over K for each fixed I, the sum over K of nu H I K, it's bounded by P star EI plus 2 epsilon, we get that this sum is less than or equal to the sum of P star EI plus epsilon divided by 2 to the power I. Well, and this is equal to the sum of P star EI plus epsilon. So we proved that P star of E is less than or equal to the sum of P star of EI plus epsilon. Since this holds for every epsilon, we obtained the claim that we were looking for, which means that P star of E is less than or equal to the sum of P star of EI. And therefore, the third property of an outer measure is fulfilled, and this proves that P star is indeed an outer measure. So, we proved the first step, in which we introduced P star, and we proved that P star is an outer measure. So now the second step consists in introducing a family of subsets which are called the measurable subsets. So M will stand for the measurable subsets. And here is its definition. So a set A will belong to M if A divides correctly every set. This means in the sense of the P star measure. So this means precisely the following. I'll say that a subset A of omega is in the class M, is measurable, if for all subsets E of omega, we have that mu star of E, it's equal to P star, it's equal to P star of E intersection A plus P star of E intersection A complement. So this means that if you take any set, E, and you divide this set with the set A, the outer measure of E, it's equal to the outer measure of the first set plus the outer measure of the second set. So here is the definition of M. And what we want to prove, two assertions. First, that M contains the algebra, and then that M is a sigma algebra. One remark. There is one inequality here which always holds. Indeed, E, it's contained in E intersection A union E intersection A complement. Since P star is an outer measure, it follows that by the subadditivity, So here it's a finite subadditivity. We have only two sets, but you can imagine that you complement this union with empty sets to have a countable and just to apply the subadditivity to this countable family of sets. And if you recall that P star of the empty set is 0, what you get from the subadditivity is that P star of E is less than or equal to P star of E intersection A plus P star of E intersection A complement. Right? So, in order to prove this identity, we only need to check that P star of E is greater than or equal to the sum. So this is what we'll need to check always, because the reversed inequality holds always for any set A and E. So let's prove that M contains the algebra and that M is a sigma algebra. So the first point is to show that the algebra is contained in the set M. So for that, let's assume that A is an element of the algebra. And we have seen that now we fix a set E, and we have to show that P star of E is greater or equal than P star of E intersection A plus P star of E intersection A complement. So this is the inequality we have to prove in order to show that A belongs to the set M. Well, observe that this inequality holds trivially if P star of E is equal to plus infinity. So I may assume without loss of generality that P star of E is finite. Well, if P star of E is finite, I can find a covering which almost attains this infimum. This means that given an epsilon which is positive, I can find a covering EI of the set E. So which means that, let me recall once again, that EI belongs to the algebra for each I, and that E is contained in the union of EI. So I can find such a covering in such a way that P star of E is less or equal than the sum of new EI plus epsilon. I'm sorry. I can find a covering, so P star of E is the infimum, so it's always less or equal than this particular sum, which is the value for that covering, but I can find a covering which almost attains this infimum in such a way that the sum is less than or equal to P star of E plus epsilon. Right? So this is possible because P star is finite by assumption. Well, that's nice, because here I have a covering of the set E. So if I take EI and I take the intersection of EI with A, since A is an algebra, EI intersection A also belongs to the algebra. So here's an observation. EI intersection A belongs to the algebra. And since EI, the union of EI covers E, E intersection A, it's also contained in the union of I greater or equal than 1 of EI intersection A. Therefore, EI intersection A, it's a covering of the set E intersection A, which means that P star of E intersection A is less than or equal to the sum of nu ei intersection A. Well, by similar reasons, replacing A by A complement, we can get that P star of E intersection A complement is less than or equal to the sum of nu ei intersection A complement. Right? So now we can conclude. It's enough to, so remember what we want to prove. We want to prove that inequality. So we'll just sum these two expressions to get that P star of E intersection A plus P star of E intersection A complement is less than or equal to the sum of these two expressions. So it's less than the sum for E greater or equal to 1 of nu ei intersection A plus nu of ei intersection A complement. But now nu, it's sigma additive, so it's additive. So I can just, since these two expressions are have no intersection or disjoint, the sum it's equal to the sum of nu. So the union of these two sets is just ei. And the sum of nu of ei, by construction of this covering of E, it's less than or equal to P star E plus epsilon. So you see that we just proved that P star E intersection A plus P star E intersection A complement is less than or equal to P star E plus epsilon. This holds for any positive epsilon, so we can send epsilon to 0 to conclude that indeed P star of E intersection A plus P star of E intersection A complement is less than or equal to P star E, which proves that the algebra it's included in M, which means that every set in the algebra is measurable. Well, we proved that every set in the algebra is measurable. Now let's prove the second property of M is that M is a sigma algebra. So we need to show three properties of M. The first one is that the empty set, or omega, belongs to M. So let me just remind you what we need to show in order to prove that omega belongs. We have to show that for any set E, psi star of E, it's equal to P star of E intersection omega plus P of P star of E intersection omega complement. Well, but this identity is clear because omega complement, it's the empty set. So this expression is just equal to the empty set. And we have seen that P star of the empty set is 0. While here we have E intersection omega, which is E. And therefore we get that P star of E is equal to P star of E, which is a tautology. And therefore omega belongs to the set M, so omega is measurable. Then the first property which we need to prove for M is the fact that it's closed by complement. So let's assume that A belongs to M, and we want to prove that A complement belongs to M. But this is clear because the definition of M, it's symmetric with complements. More precisely, if we want, so what does that mean? What does it mean that A belongs to M? It means that for every set E, we have that P star of E, it's equal to P star of E intersection A plus P star of E intersection A complement for every E. Right? So to say that A is measurable is to say that for any subset E of omega we have this identity. But if this identity holds, it holds also for A complement, since this expression is symmetric by complements, and therefore A complement belongs to M. So the fact that M is the set of measurable sets, it's closed by complement, it's obvious. So what's not so obvious is that M it's closed by countable unions. So let's assume that Aj belongs to M for all j greater or equal to 1, and we want to show that the union of Aj belongs to M. So this step will be performed in the proof of this assertion will be performed in 2 steps. We will first show that M is closed by finite unions, and then we will show that M is closed by countable unions. So let's first show that if A and B belong to M, then A union B belongs to M. Well, if A belongs to M, so let's fix a set E, subset of omega, and what we need to prove is that P star E it's greater or equal than P star of E intersection A union B plus P star of E intersection A union B complement. So this is what we want to prove. But we know that A and B belong to M. So we know that since A belongs to M, we know that P star of E it's greater or equal than P star, it's in fact equal to P star of E intersection A plus P star of E intersection A complement, and I will write that E minus A. So this identity holds because A is measurable. Now let's use the fact that B belongs to M, and as a test set I will use E minus A. So P star of E minus A, since B belongs to M, it's equal to P star E minus A intersection B plus P star E minus A intersection B complement, which is minus B. Well, now I can replace P star E minus A in this identity to get that P star of E it's equal to P star of E intersection A plus P star of E minus A intersection B, and this last set observe that it's E minus A minus B. So I can rewrite this set as E minus A union B, right? You are taking out from E A and then B. So this is equal to P star of E minus A union B, which is also E intersection A union B complement. And if you observe that you go back to the expression which we need to prove, you observe that you have on the left side P star E, and on the right hand side you have already this term. So in order to conclude the proof, what we need to show is that the sum of these two terms is less than or equal this term. Right? If you can prove that these two terms, what we need to show, we have this identity. So let me take back what I just said. We have this identity, so what we need to prove is that this expression is greater or equal than P star of E intersection A union B plus P star of A minus A union B, right? So if we are able to prove this inequality, right, we would have proven that P star phi is greater or equal than the sum, which is exactly what we want. So since this term is equal to that one, to conclude the proof, what remains to be done is to show that P star of E intersection A union B is less than or equal to this sum. So let me rewrite it here. What remains to be done is to show that P star of A intersection A union B is less than or equal to P star of A intersection of E intersection A plus P star of E minus A intersection B, right? And to prove this inequality, we will use the subadditivity. So what I claim is that E intersection A union B, it's contained in E intersection A union E minus A intersection B. Right? If we prove that this set is contained in this union, we can use the subadditivity to obtain that P star of this set is less than or equal than P star of this set plus P star of this set, which is exactly what we have to prove. So it remains to show this relation. And what we will do, we will consider this set, X E intersects A union B. This is equal to, if I take this set and I intersect it with A, union E intersection A union B intersection with A complement. So let's see what we have here. Well, here we have the intersection with A, so let's distribute this intersection in these two sets. So we have here the intersection of E and A, while in this one, this intersection A union B with A gives you A, so this expression is just E intersection A. Now, let's go to this other one. We have here the intersection of E with A complement, and now the intersection of that with A complement intersection A union B, which is B. But A intersection A complement, it's A E minus A. So this is E minus A intersection B. So indeed, what we obtain is that E intersection A union B, it's contained, well, in fact, it's contained in E intersection A, which is this term, union E minus A intersection B, which is this term. So this reasoning proved that relation. From that relation, we obtained this inequality, which is what was missing in the proof. So this concludes the proof that M it's indeed closed by finite unions. So we have seen that the family M is closed by finite union, and now I claim that in fact this family is closed by countable union, right? And by proving that, we conclude the proof that M is a sigma algebra. So in order to prove that it's closed by countable union, assume that we have a family AG, which is in the set M, and we want to show that A, which is the union of AJ for j greater or equal than 1, belongs to M. And in order to prove that A belongs to M, we have to show that for any set E, so let's fix a set E, a subset of omega E, we have to show that P star of E it's greater or equal than P star of E intersection A plus P star of E minus A. So this is what we need to prove. And we know already that M is closed by finite unions. So if I stop this union at any n, I know that this union belongs to M. And we will use that. So this set E is fixed. So we know that P star E, it's equal to P star of E intersection the union of AJ, j from 1 to n, plus P star of E minus the union from j from 1 to n of AJ. So this we know already because M it's closed by finite union, and each of these sets AJ belong by assumption to M. Well, here this union it's clearly contained in the countable union. Therefore, if I take E minus, I get that this set contains, so this set contains E minus the global union, which is E minus A. Right? So E minus A is contained in this union, and by monotonicity of the outer measure P star of this set is less than or equal to that one, so we get just by monotonicity that this sum it's in fact greater or equal than P star of E intersection the union from 1 to n of AJ plus P star of E minus A. Now, all the problem is to pass to the limit in this set n. And for that, we will use the fact that we have that M it's closed by finite union, so that M it's an algebra, to redefine this union as a union of finite sets. So let me define F1 to be A1, F2 to be A2 minus A1, and so on up to Fn, which will be An minus A1 union An minus 1. Right? So, first, it's clear that the union of Aj from 1 to n, it's equal to the union of Fj from 1 to n. Then, it's also clear that all these sets F are disjoint 2 by 2. So, it's also clear that Fj intersection Fk, it's equal to the empty set if J is different from K. So, we have a disjoint union of sets. And finally, it's also clear that Fj belongs to M because we have seen that the set M, it's closed by complement and it's closed by finite union, so it's also closed by differences. So since each of these sets A belong to M, these sets F, J also belong to M. Therefore, what we have up to now is that I can replace this union by the union of Fj. So up to now, we proved that P star E, it's greater or equal than P star of E intersection the union of Fj, J from 1 to n, plus P star of E minus A. Here, to obtain this identity, I just use the fact that the union of Aj is equal to the union of Fj, and I use this symbol, sum, because the sets Fj are disjoint 2 by 2. Now, what I claim is that P star of E intersection the sum from 1 to n of Fj, that this is equal to the sum from 1 to n of P star E intersection Fj. So I claim that we have this identity, and we will prove this identity by induction. So let's start with n equal to 1. For n equal to 1, we have here on the left-hand side E intersection F1. On the right-hand side, we have E intersection F1. So it's a tautology. So this identity clearly holds for n equal to 1. So now let's assume that it holds for n, and let's prove it for n plus 1. So to prove it, to go from n to n plus 1, now we will use the fact that the sets F, K belong to M. Right? And we are using the fact that we have seen that because we have already proved that M is an algebra. So, since Fk belongs to M, let's use k equal to n plus 1, and let's use as test function, as test set, the set E intersection the sum or the union from 1 to n plus 1. So, as Fn plus 1 belongs to M, we have the following identity, that P star E intersection the union from 1 to n plus 1 of Ej, of Fj, that this is equal to P star of this set intersection Fn plus 1 plus P star of this set, E intersection the sum from 1 to n plus 1 fj, intersection fn plus 1 complement. Right? This identity holds because the set fn plus 1 belongs to M. Now let's see what we have on the right-hand side. Well, all these sets fj are disjoint. So if I take the intersection of fn plus 1 with this sum, only remains the last one, fn plus 1. So this term here, it's equal to p star of E intersection fn plus 1, because all the other intersections are just empty because these two sets, the family F is formed by disjoint 2 by 2 sets. On the other hand, if I take the intersection of fn plus 1 complement with this sum, observe that, well, the intersection with fn plus 1 it's empty, while since the intersection of fj with fn plus 1 it's empty, this means that fj is contained in the complement of fn plus 1, which means that the intersection of fj with the complement of fn plus 1 is just fj. So this expression, it's equal to p star E intersection the sum, but now from 1 to n of fj. So we just proved that p star of E intersection the union from 1 to n plus 1 of fj, it's the last term plus the p star of the first n terms. Now we can use the induction assumption to rewrite p star of this intersection as the sum of p star and to obtain the claim for n plus 1. So this concludes the proof by induction of this identity. Right? Here I can use the induction assumption to move this sum from the inside to the outside, and what we get is exactly the claim for n plus 1. So this is the proof of the claim. Now we will use this claim to conclude the proof that M is closed by countable unions. Right? The claim allows us to rewrite this inequality as a sum from 1 to n of p star of E intersection fj plus p star of E minus A. Right? So what we have up to this point is that p star of E is greater or equal than the sum from 1 to n of p star E intersection fj plus p star of E minus A. And this is true for all n, so we can send n to infinity to get the same inequality for the sum j greater or equal than 1. And now we can use the subadditivity to claim that this is greater or equal than p star of E intersection the union of fj plus p star of E minus A. Right, so here is just the subadditivity. Right, we have the p star of the union, it's less than p star of each individual set. But the union of fj, by construction of our set fj, if you recall the definition of the sets fj, coincides with the union of aj, and the union of aj is just A. So this is equal to p star of E intersection A plus p star of E minus A. And this is exactly what we wanted to prove. We wanted to prove that p star of E intersection A plus p star of E minus A was less than or equal to p star of E. So this is exactly what we proved, and this concludes the proof that M it's indeed a sigma algebra. In particular, since it contains the algebra, M contains the sigma algebra generated by the algebra. So let me write it here, what I just said. So, or maybe let me summarize what we proved. We proved, one, that the algebra is contained in M. Now I just proved that M is a sigma algebra. And so it follows from these two assertions that M in fact contains the sigma algebra generated by the algebra. So this is what we proved up to now. So we just proved that M is a sigma algebra which contains the sigma algebra generated by the algebra. So now the third step will be to show that if you consider P star restricted, so P star has been defined for all subsets, but if you consider its restriction to M, then its restriction is sigma additive. And we proved, so we have also to prove that it's an extension, so we will also prove that P star of A is equal to nu of A for all A in the algebra. Right? So we'll prove that P star it's sigma restricted to M, it's sigma additive, and we will prove that its restriction to the algebra it's the measure or the function from which we started from. So let's first prove that P star of A it's equal to nu of A for all A in the algebra. Well, this proof is very similar to the proof that P star of the empty set is equal to 0. First, let's show that P star it's less than nu of A. Well, that's clear because if I take A, the empty set, and so on, I get a covering of the set A by elements of the algebra. So by definition of P star of A, it's less than or equal to the sum of this covering. So let's call E1, E2, and so on this covering. But nu of the empty set is 0, and nu of E1 it's just nu of A. So we trivially get that P star of A is less than or equal to nu of A, just because P star it's an infimum over coverings which contain the trivial covering A, empty set, and so on. So to prove the reversed inequality, the argument it's also not very difficult. Well, what we have to show is that nu of A is less than or equal to the sum of nu of Ej for any family Ej whose elements belong to the algebra and which forms a covering of the set A. So what we need to show is that this inequality holds if you have such a family. And well, what we will do, we will start with this family EJ, we will construct a family of elements of the algebra which are disjoint 2 by 2 and which contain the set A. So this is exactly the construction we did a minute ago. So F1 will be E1, F2 will be E2 minus E1, and in general Fn will be En minus E1 union En minus 1. Okay. Then we have exactly the same observations I did a minute ago. So these sets Fj, they all belong to the algebra because the sets E belong to the algebra. The union of Fj, it's equal to the union of the sets Ej by construction. Then these sets F are disjoint 2 by 2. So Fj intersection Fk, it's empty set if J is different from K. So since A it's contained in the union, A it's also contained in the union of Fj. Now, this means that A it's equal to the union of Fj intersection A. Right? And here we have an identity between an element A of the algebra and a countable union of elements of the algebra. Right? A belongs to the algebra, and each Fj belongs to the algebra. So we can use the sigma additivity of nu here. So we have that nu of A, it's equal to the sum. So here is the point in the proof where we are using the fact that nu is sigma additive on the algebra, in the algebra. So this follows by sigma additivity, and it was very important to have an element of the algebra written as union, countable union of elements of the algebra. So we have this inequality, but now Fj, by definition, it's contained in Ej. So Fj intersection A, it's contained in Ej. So this is by monotonicity of nu, it's less than or equal to the sum of nu of Ej. And this is exactly what we wanted to prove. We wanted to prove that nu of A is less than or equal to nu of Ej. So this is true, this holds, this inequality holds for any covering of the set A by elements of the algebra. Since it holds for any covering, it also holds for the infimum of all such coverings, and the infimum over all such coverings is exactly P star of A. So this proves that nu of A is less than or equal to P star of A, right? So we proved that so this holds for all coverings. So this implies that, let me write it to make it clear. So this implies that nu of A is less than the infimum, if I now take the infimum over all coverings of the set A, of the sum of nu Ej, but this is by definition P star of A. So we have proved that nu of A is less than or equal to P star of A, which together with the first assertion we proved gives you the identity. So indeed, P star is an extension of nu. So P star restricted to the algebra is exactly equal to nu. So now what we have to prove is that P star restricted to M is sigma additive. So what we need to show, well, take a sequence aj in M, disjoint 2 by 2, and we want to prove that P star of the union of aj it's equal to the sum of P star of aj. Right. Well, we have seen that P star it's an outer measure, so P star it's sub-additivity, it's sub-additive. So what we have is that P star of the union of aj is less than or equal to the sum of P star of aj. Right, so this first inequality follows just by sub-additivity. Now we have to prove the reversed inequality. Well, for that, what we will use it's first that P star it's monotone. So this means that if I take the countable union of these sets, this is greater or equal than P star of the union from 1 to n of aj. And now I claim that P star of this union, since these sets aj all belong to M and are disjoint 2 by 2, by just repeating the argument of the claim which I proved here in this blackboard 2 minutes ago, what we have is that we have this identity, right? Remember, we proved this identity by taking E intersection such an union, where I was calling these sets A, F, and we proved that by induction this identity. So it trivially holds for n equal to 1, and we proved by induction that it holds for any n. So the same argument, taking E to be the set omega, gives you this identity. So up to now, what we prove is that the P star of the countable union it's greater or equal than the sum up to n. This holds for any n, so you can just send n to plus infinity to get that P star of the union it's greater or equal than the sum of the P stars, which is the reversed inequality, and this gives you the identity, and therefore this proves that P star restricted to the class of measurable set is indeed sigma additive. So we are almost done because we obtained our extension. Right? We have M, which is a sigma algebra which contains the sigma algebra generated by the algebra. P star, it's sigma additive on this sigma algebra, and it's an extension because if you restrict it to the algebra, what we get it's exactly nu. So to conclude, what do we need to prove? Well, we need to prove that this extension is unique, right? If this extension were not unique, we don't know exactly what we are talking about. And so the last step in the proof consists in uniqueness proof, and we won't prove uniqueness on the set M, but we'll prove uniqueness on the sigma algebra generated by the algebra, and we will require a further assumption. So the last step, which is uniqueness, can be stated as follows. Well, let's assume that we have two measures, or two functions, mu1, mu2, defined on the sigma algebra generated by an algebra. And let's assume that mu1 restricted to the algebra, it's equal to mu2 restricted to the algebra. And let's assume that the set omega is sigma finite. So here is a new concept. Set to be sigma finite means the following, and this will depend on the measure, so let's say mu1 sigma finite. So we'll say that omega is mu1 sigma finite if there exist sets ej which are increasing to omega. So this means that ej, it's contained in ej plus 1, and the union of ej, it's equal to omega, and such that mu1 of ej, it's finite for all j. So you see, mu1 of omega can be infinite, but what this assumption requires is that, well, you can write omega as a union of sets which have finite measure. Right? So you can decompose omega as a union of ej, and each set ej has finite mu1 measure. And these sets ej, we will require them to be in the algebra. So these sets in this condition, in this last step. So the definition doesn't require ej to be element of the algebra. So the definition of, let me make it clear, the definition of sigma finiteness of a set omega just requires the existence of these sets aj in the sigma algebra in which mu1 is defined. But in this last step, we will require additionally that these sets ej, which appears in this decomposition of omega, to be all in the algebra. And since they belong to the algebra, the set omega, it's sigma finite for mu1 if and only if it's sigma finite for mu2, because mu1 and mu2 coincide in the algebra. So I'm assuming for the uniqueness that you have two functions which are defined in the sigma algebra generated by the algebra, that they coincide in the algebra, and that the set omega, it's sigma finite with respect to mu1 and mu2 with a decomposition which belongs to the algebra. And what I claim is that then mu1, it's equal to mu2. So it will follow from this last assertion that the measure p star, the function p star which we defined on M, if we restricted to this p star to the set fa, so to the sigma algebra generated by the algebra, if we started from a measure nu for which omega is sigma finite with respect to nu, then the extension is unique. And this will conclude our proof of the extension. So we started from a function which is sigma additive on an algebra. We were able to extend this function to a sigma algebra which contains the sigma algebra generated by the algebra. It's sigma additive in this sigma algebra. It's an extension, and the extension to FA. So note that we are not claiming that the extension to M is unique. just claiming that the extension to the smaller set f of a is unique. So let's prove this last step. So the proof will rely on the concept of monotone classes. So let me define what a monotone class is. So let's say that we have a set omega, and we have a class, let's call it G, of subsets of omega. So I will say that G is a monotone class if G fulfills two conditions. It should be closed by increasing limits, in the sense that assume that Aj belongs to G for j greater or equal than 1. Assume that this sequence is an increasing sequence, so that Aj is contained in Aj plus 1. Then we will require A, which is the union, so the increasing limit of this sequence Aj, to belong to G. So we are requiring in this first condition G to be closed under increasing sequences. And the second condition is just saying that G is closed by decreasing sequence of sets. So let's here assume that Bj belongs to G for j greater or equal than 1. Assume that Bj contains Bj plus 1, so that this sequence, it's a decreasing sequence. I forgot here to, this is then. So we will require that if we have a sequence of sets in G, which is decreasing, then the limit of this sequence, which is just the intersection, will require the intersection of these sets Bj to belong to G. So G will be called a monotone class if it's closed by increasing sequences and by decreasing sequences. Okay. Well, as we have seen for sigma algebras, so now here is an assertion which is a very simple assertion, is the following. Suppose that I have a family G alpha, which are monotone classes of subsets of some set omega. Right? Then what I claim, and here the index alpha belongs to some set I, and I'm not imposing any condition on the family of indices. So what I claim is that the intersection over alpha in I of G alpha is also a monotone class. And that's very simple. I leave it to you to check that indeed this intersection is a monotone class. Then this allows us to speak of the smallest monotone class which contains a set. So let's say that we have a family C of subsets of some set omega. I can denote it by G of C, the smallest monotone class which contains C. And this is just what? Well, you take all monotone classes which contains C, you take the intersection over all these sets, and you get, by the first assertion, that this is a monotone class, And it's the smallest monotone class because any monotone class which contains C, it's here and therefore contains G of C. So once you prove this assertion, you can introduce the notion of a monotone class which is generated by a class C of subsets of omega. So this will be called the monotone class generated by the class C. Note that we are not doing any assumption C. C can be just anything. And also that this intersection is non-empty because, of course, the family P of omega, so all subsets of omega, it's clearly a monotone class and it contains C. Therefore, this intersection is an intersection over a non-empty set, so it makes sense. And we have here so the notion of monotone class generated by a class C. Well, once we have introduced this concept, here is a lemma which will be extremely important in all these lectures and whose proof will be given in the next lecture, because I would like to conclude the proof of the extension. So here is the lemma. And as I said, this lemma is extremely useful. It will be used several times in these lectures. So it's a very important result. So let's say that we have a family of subsets of omega, which is an algebra. And let's denote it by M of A, the monotone class generated by A. Let's denote it by F of A, the sigma algebra generated by A. So what I claim is that these two sets are equal. So the monotone class generated by an algebra A, it's equal to the sigma algebra generated by an algebra A. So this result, it's, as I said, extremely important, and I'll give you proof in the next lecture. So let's prove uniqueness. So what we have two measures, mu1, mu2, defined on a sigma algebra generated by an algebra. And these two algebra coincide, these two functions coincide on the algebra. And omega is sigma finite in the sense that omega can be written as a union of Ej such that Ej belongs to the algebra and mu1 of Ej, which is equal to mu2 of Ej because mu1 and mu2 coincide on the algebra, it's finite. So here are the assumptions, and what we want to show is that in fact mu1 and mu2 coincide in f of a. So let's go to the proof. Well, let's fix n, and let's represent by, let's say, h or b. B will be the elements of the sigma algebra such that u1 of E intersection En, it's equal to mu2 E intersection En. Right? So I fixed n. So maybe let me show that B, this class of functions, depends on n. So it's all sets in the sigma algebra for which we have that mu1 of E intersection En is equal to mu2 of E intersection En. Note that these two quantities are finite. Now, I first claim, well, of course, Bn it's contained in Fa, because we are only taking sets in Fa. What I want to prove is that Bn it's in fact equal to f of A. And how shall we prove that? Well, we will use the lemma I mentioned about monotone classes. So first observe that Bn contains the algebra A, right? If you take an element of the algebra, let's say that E belongs to the algebra, since En belongs to the algebra, E intersection En belongs to the algebra, and mu1 and mu2 coincide in the algebra. So it's clear that A, the algebra, is contained in Bn. Now, I claim that Bn is a monotone class. Here is the power of the lemma I just stated. And I wanted to state this lemma here inside these lectures to show the importance and the usefulness of this result. So it's very easy to show that Bn it's a monotone class, and it's very difficult to show that Bn it's a sigma algebra. But since the monotone class generated by an algebra it's equal to the sigma algebra generated by the algebra, we have here a very simple way to show that Bn it's in fact the contains the sigma algebra, or since it's contained, it's equal to the sigma algebra generated by the algebra. So let's see what I just said in few words in more details now. What I claim first is that Bn it's a monotone class, and it's here that we will use the fact that omega is sigma finite. So to show that Bn it's a monotone class, what do we need to prove? Well, we need to prove two properties of Bn. So let's take a sequence Ej, it's not very well chosen. Let's take Aj, a sequence in Bn which increases. And let me represent by A the union of Aj. And to prove that Bn it's a monotone class, I have first to prove that A belongs to Bn. But this is very simple, because this is just follows from the fact that mu1 and mu2 are sigma additive, and therefore they are continuous from below, right? So mu1, we know that Aj belongs to Bn. This means that mu1 of Aj intersection En it's equal to mu2 of Aj intersection En. This is just by definition of Bn. Since Aj belongs to Bn, these two quantities are equal. Now, mu1 and mu2 are sigma additive functions defined on the sigma algebra. So, since they are sigma additive, they are continuous from below. Aj it's increasing to A, so as I take the limit in J in this equation, I get that it converges to mu1 of A intersection En. While this one will converge to mu2 A intersection En, and since each term of the sequence is equal, their limit is also equal, and we get that mu1 of A intersection En is equal to mu2 of A intersection En, and therefore that A belongs to Bn, because A is certainly an element of the sigma algebra, because each one is an element of the sigma algebra, and we have the identity. So this proves that Bn it's closed by increasing sequence. So now we have to check that Bn it's closed by decreasing sequence. So let's now take Bj, a sequence of sets in Bn, and let's assume that bj decreases, and let's call b the limit. So b is the intersection of bj. And to show that Bn is a monotone class, we have to prove that B belongs to Bn. But again, this is very simple. Well, since Bj belongs to Bn, we know that mu1 Bj intersection En it's equal to mu2 of Bj intersection En. Now we use again the fact that mu1 and mu2 are sigma additive to claim that they are continuous from below at any set. And it's here that we need to use the fact that the set omega is sigma finite. So in order to pass to the limit, we need to guarantee that this sequence, it's finite starting at some point, so that there is an index j for which this expression is finite for some j, and the same thing on the right. Right? Remember that continuity from below required the finiteness of the sequence. So here we know that this value is finite because mu1 of En is finite. But without this assumption, we couldn't use the sigma additivity to use we couldn't prove that this sequence converged because it might be equal to plus infinity at all j's. So let me state it again. Since mu1 of En is finite, since mu1 is sigma additive, and since this sequence decreases to B intersection E1, this sequence converges to mu1 B intersection En. Right? So let me say it again. Bj is decreasing to B, so Bj En is decreasing to B intersection En. Since mu1 of this set is finite, we can pass to the limit to obtain that this sequence converges to that. The same thing happens for mu2, and therefore we get that mu1 B intersection En is equal to mu2 B intersection En, and therefore B belongs to Bn. So that Bn is closed by a decreasing sequence, which proves that Bn is a monotone class. So we proved that Bn is a monotone class and that Bn contains the algebra. Therefore, Bn contains the monotone class generated by A. So I'm representing by M of A the monotone class generated by A. And we have seen that the monotone class generated by A coincides with the sigma algebra generated by A, because A is an algebra. Therefore, Bn contains Fa, but Bn it's also contained in Fa, so Bn it's equal to Fa. And here I propose to you to try to prove that Bn is a sigma algebra. Try to prove that Bn is closed under countable union. So you'll see that, it's quite a difficult problem, and therefore the lemma which guarantees this identity is extremely useful because it's very easy to prove that Bn is a monotone class, as we have just seen. So we proved that Bn is equal to Fa, and now we can conclude our argument that mu1 and mu2 coincide on the sigma algebra. So let me erase just this piece. Right? So I just proved that Bn is equal to f of A. Right? So I want to show now that mu1 of A it's equal to mu2 of A for any A in the sigma algebra. All right, so let's take A in the sigma algebra. Since the sigma algebra coincides with Bn, I know that A belongs to Bn. Well, but if A belongs to Bn, this means that mu1 of A intersection En is equal to mu2 of A intersection En. But now, En, it's a family which is increasing to omega, so I can pass to the limit here using the fact that mu1 and mu2 are sigma additive. They are continuous from below, so I can send n to infinity to conclude by using the continuity from below of mu1 and mu2 that mu1 of A is equal to mu2 of A. Right? And this concludes the proof of the uniqueness. So we conclude the proof of the theorem which is written in this blackboard. This, let me conclude with some remarks. This theorem, it's called Caratheodory theorem. Note, it's a very concise proof of the extension, of the fact that we can extend a function which is sigma additive in an algebra to a function which is sigma additive in the sigma algebra generated, that this extension is unique. You can see in the exercise I will propose that this condition of sigma finiteness, it's indeed needed, that the extension may not be unique if you don't require the sigma finiteness. And also, a remark which is important is that this set M, so that in fact we constructed the extension in this set M, which is bigger than the sigma algebra generated. In fact, we will see in the next lectures that in some examples, this sigma algebra is strictly bigger than the sigma algebra generated by A. And that this sigma algebra depends on the measure from which we started from, right? We started from some measure nu. We defined P star, and the definition of M was depending on P star. So this, if you consider two different measures, nu1 and nu2 defined in the same algebra, nu1 and nu2 which are sigma additive, the set M1 which is obtained from nu1 and the set M2 which is obtained from nu2 might be different. So they will depend on nu1 and nu2. So, but you still have a function which is sigma additive defined on this set, which depends on the measure and which can be strictly bigger, strictly larger than the sigma algebra generated by the algebra. So this concludes our extension. So we've seen in the previous lecture that it's easy to extend a function which is sigma additive defined in a semi-algebra to the algebra. And now with Caratheodory's theorem, we have a way to extend this function which is sigma additive in an algebra to a function which is sigma additive in the sigma algebra. And in the next lectures, we will start to extend it to an even larger set, this measure. And on the other hand, we will start applying this theorem to the problem which we started with, which means the length. So we will apply this theorem to the case of omega equal to the line and taking as starting semi-algebra the semi-algebra formed by the intervals. So this will be the content of the next lectures.